Yeah, last week we spent all time discussing Kant's philosophy. No, I don't regret. I think it certainly deserves, and we can even talk much longer only about Kant. I don't want, of course, to to reduce our course to Kant. Opa, sorry. Okay, now it should work. So if you have probably some more questions, things discuss, because I planned also to talk about non-Euclidean geometries, and that's what I'm going to talk now. Right. So what is relation between Kant and non-Euclidean geometries? Perhaps I should explain. It might be not evident by itself. No, thing is that I would say already in late 19th century and beginning of 20th century, Kant's philosophy of mathematics somehow ceased to be mainstream, right? Because it's very long was a mainstream, no, at least in certain circles. Of course, this notion of being mainstream is not strictly defined unless we do some sociological research that I think was never done, best of my knowledge. Of course, there were some other developments, people who just did something, say, related, what we may qualify as philosophy of mathematics, and just ignoring Kant, or certain other people actually, but that's more specifically, who try to object Kant very seriously, like Tredenlenburg, who promoted, say, Aristotle. No, I don't think we are going to look into all these developments, because it's rather belongs to history of philosophy, and it's interesting, I think important, but still rather specific chapters. So I don't think I'm going to talk about this. However, just simple point is this, that many people, including, for example, Bertrand Russell, that I'm going to talk maybe later today, if you have time, or next week, it's already, he's seen very much as one of founding fathers of what is analytical philosophy, and this is the mainstream philosophy today. So he just dismissed Kant using this argument that Kant somehow didn't take into account non-Euclidean geometries. Of course, he couldn't do that. They were really invented later, even if there were some developments, I'll tell you in a minute, and actually much earlier than Kant, that kind of led to these discoveries. So what was the argument? The argument was that, as we've seen, Kant assumed, again, very much simplified, right, that mathematics is in some sense in naturalistic interpretation, which is by itself problematic. We may say that mathematics is just wired in, say, human brain, right? That mathematics is a way we represent the world, how it is. Representation is actually Kant's word, translated into English. Yeah, so as we discussed already last week, I remind you, right, that he strictly pursued that point that mathematics is a priori. That means that it's not something that we learn from experience, even if, of course, he could admit that experience somehow boosts, right? Somehow triggers our mathematical thinking, but it's not really the real source of mathematical thinking, right? And mathematical thinking, whatever is its source, actually Kant perhaps even didn't try to answer that question, right? He rather just described that it's kind of a conceptual scheme that is, in some sense, is a set and justified, maybe not set psychologically for individual, right, who might need a lot of experience simply to learn mathematics, as just to learn anything. However, if we think how mathematics is justified, right, how it's constituted, using also this philosophical term, is not in terms of experience. No, and as I try to argue, there is, I think, certain, at least strength in this argument, right? I'm not subscribing to this argument, but I think strong part of this argument that actually does not depend on Euclidean or non-Euclidean on anything is that mathematical proofs are really something different. They differ significantly, at least, or essentially, from some kind of proofs that we use, say, in physics, in any natural science, right? If someone comes up with the Pythagorean theorem simply by saying, I made this measurement, I checked many examples, and it looks like approximately is this, we would say, okay, that may be interesting observation by itself, but it's not a proof of the theorem, right? By proof of the theorem, we expect something different, and actually something that does not refer to experience in the same way in which such references are appropriate in, say, natural sciences. And that's, I think, it's true even today.
Oh,
Right?
sorry. Are you presenting something? Because I.
Not yet, not yet.
Oh, yeah. Okay. Just wanted to confirm.
Yeah, yes, I'm going to share. Yeah, and what it has to do with Euclidean or non-Euclidean geometry, no, you remember that example I showed you with the angle sum theorem, right? When we produce a additional straight line and prove the theorem about sum of internal angles of triangle. And of course, this theorem, as I mentioned, it actually depends. It's Euclidean. It's not a theorem of non-Euclidean geometry. It is a theorem of Euclidean geometry, right? And then if we really think that this thing is somehow a priori, and if you like, wired in human brain, then the possibility, the very possibility of non-Euclidean geometry just shows that that's false. And that's example, somehow it's not really convincing, right? And that was actually part of argument for people like Russell, who did simply dismissed on this line of thought only on that basis. Now, of course, there were other people who described themselves as neo-Kantians, somehow new wave of followers of Kantians. No, maybe, yeah, before we go to mathematics, I can just show you some of these people. No, my favorite is Ernest Casira. That's say late. That's already 19th century. You see, he was born in 1874 in Breslau in Germany, and then he was in the. He then immigrated. He was part of this Jewish immigration to United States. At certain point, he was at least one of most prominent German philosophers, say, in this period between the two world wars. Right. Then he was very much challenged by Martin Heidegger, who is very well known. I'm not going to actually talk about him, who kind of challenged his position being the leading German philosopher, and Heidegger was a sympathizer of Nazi, and actually he was a member of Nazi party, and so that, of course, later gave him very bad fame. However, during the period, he didn't work that way. He was appointed actually rector in, sorry, forgot which exactly university. We can look up. However, Ernest Casira, as many other people, he had to emigrate. However, unless some other people like Rudolf Carnap, for example, no, he was, say, Austrian officially rather than German, but after the Anschluss, that actually did matter. And Carnap actually made a very successful career in the United States, and again became one of, say, founding fathers of analytic philosophy. That was not the case of Casira. So he died, you see, in April in New York, just 1 month, 1 month before the victory, before the end of the Second World War. And his major works are still not translated into English. He wrote actually a lot. So he was in this rather traditional philosopher, say, in terms of his style. He wrote really long paper, and sometimes indeed you may approach him saying they are just too long. You could say all of that shorter. Yeah, maybe that stylistic difference was one reason why he somehow was not accepted very well in the United States. Another reason was, of course, that he was already well-established philosopher, right? Unlike Carnap, who made, say, who became known already in the United States. He published earlier in German, however, he was not such a major figure then, comparable with Casira. No, anyway, there are very good literature now on all this, say, circumstances, and you see that politics is involved, right? You cannot really, I don't know, even in mathematics, politics matters, but I think in mathematics it's still somehow easier, right, to make distinction between, say, purely scientific work, right, what happens in terms of, say, mathematical results, and what happens in terms of political context and circumstances where people find themselves, where they have to work. However, in philosophy, I think it's a bit more difficult, right? Because even that question of style could be politicized somehow, right? Even if, of course, he was in a sense a victim also of Nazism. He was never anything like Nazi sympathizer, unlike, say, his Martin Heidegger. But anyway, say, his career. No, on the other hand, he was not so young already, right? He was how much? Yeah, I'm not good in computing. Anyway, I think it's a very important figure, which, partly because of political circumstances, even today remains, say, no, we wouldn't say obscure, of course, but I think a more attention should be given what he was doing. So why I mentioned Ernst Casira? Because he was one among some others who described himself as neo Kantian, and who tried to somehow adopt, modify Kant's ideas to these new circumstances. Actually, important part of this was kind of introduction, say, certain historical dimension. Yeah, some scholars who are more Kant scholars than myself, they find it in Kant himself. Even frankly, I was not quite convinced of this thing. On the other hand, I never studied it really systematically. Whether we can find in Kant that's kind of historical relativism in a sense. So the idea was that, okay, it was saying something like that Kant, what Kant wrote, saying his critique of pure reason, was relevant to his time, right? Say to Newton, to analysis of science of his time. But since science develops, right, we simply need to revise it. So we shouldn't take it anything like a dogma or even last word, right? So we should rather follow Kant's method of critical philosophy rather than anything he was saying, say, positively with these unfortunate examples and so forth. So since we now gotten on Euclidean geometry, we should somehow incorporate it in this Kantian. So we should do kind of Kantian analysis in a new way. And that's basically what he was trying to do. And I think, say, interestingly, right? However, other people say Ezra, I think Russell is, he is very bright character. So I think we may choose Russell. It was not only Russell. They just say, okay, we should do something really new. We should just dismiss Kant and, go ahead. However, as often actually happened in history, what they considered was new, it was new in many respects. However, in certain other respects, I'll try to show you, it actually was a return to some more traditional, say, Aristotelian ways of thinking that Kant and Kantian would, in their turn, would consider as outdated. History is actually complicated. Right. So let's, that just explains the relevance of this Euclidean, non-Euclidean thing, because of course it was not the only important thing in mathematics of 19th century. I think 19th century is really very rich to mathematical results, to many results or open, there are many open problems like Riemann hypothesis, for example, which works in 19th century. So coming to 19th century, we much more in say today mathematics than earlier. No, right. So okay. So let me talk about this particular, say, story, because even it was not the only story that really changed minds of many mathematicians and philosophers about mathematics in general. Certainly it was a very, very important event that contributed to this to these changes. Okay, so let me wait, I try to show you now one book, which I think is still the best book on the subject ever written, except, yeah, at first I thought it might be said not far outdated at all. However, now I would say it's still a bit outdated because it simply does not present well, say, the late 19th century as a development, say. Yeah, wait, I should ask someone to, yeah, Evgeny, I mute you, okay? So otherwise we can all hear your keyboard. Okay, no problem.
Oh, sorry.
No problem. Oh, okay. Yes. Can you see the title?
Yes.
Okay. Okay, so let's. So book is actually was first published in 1906, I think, in Italian. The author is called Roberta Bonola, and it's called Non-Euclidean Geometries. It's actually it's old book, but somewhere. Yeah, here it's Italian. Wikipedia says, yeah, 1906, and it's still republished. There is Russian translation also, and what I show you is actually a is English translation, but it's rather early English translation of 1912, right? Yeah, let's yeah, let's look. So it's still, I think, very good book just to learn about, 1912. In terms just of history of the subject, and a very good thing of this book, it's not really prejudged about how about certain vision of all this story, right? I think this is indeed the advantage in that case, because it's you may read just about history rather than, and many modern textbooks, they really just imply some sort of 20th century optics, which I think I would say distorts the real history. So let's first just say, what is the problem? Yeah, and the problem is about so-called fifth postulate in Euclid's element. And if you remember, because many people confuse it now with, let's say, equivalent proposition. Can you see this whiteboard now?
Yes.
Good. Yeah. So I just remind you how it states in Euclid. Probably I did it already once. So this Euclid's postulate precisely says this. I stop my video, otherwise my computer doesn't allow me to use this planchette. Well, okay. So it just says, if we have configuration like this, right? Two straight light intersected by third straight light, and we have a no, I need not these internal angles, but these ones, right? And I have in angles like alpha and beta, such that alpha plus beta together. Now, I remind you, in Euclid, we are not talking about measure of angles, right? But rather about angles themselves. But that's not important now. So it's strictly smaller than pi, right, in radian. Measure than two right angles. Then, so that's a condition. Then these lines being produced continuously, and that's, by the way, second postulate, I remember, right? Second postulate says that every line, and line, again, I remind you, in Euclid is a segment, actually, right? He doesn't consider infinite line as an object, but there is the second postulate, that says that any such line can be continued indefinitely. That's what it says. Then you may, of course, think what it does mean exactly. Right. So if these two lines are continued according to the second postulate, right, then they eventually intersect. And that was what that fifth postulate, so it's a fifth postulate says. And as I mentioned, if you even compare this fifth postulate with other postulates, you see it's kind of complicated, right? It's not like first three postulates, which basically describe what is construction by ruler and compass. Then there is the strange, a little bit fourth postulate that says that all right angles are equal to each other. Right. Some people say it's actually late interpolation, that real core are only first three postulates. So it's indeed rather obvious that this postulate is not that good, right? So if we really stick to this traditional idea that axioms and postulates should be somehow primitive and self-evident, right? Recall I told you postulates actually are not statements, right? But rather rules. No, if you like that, you may also interpret as a rule, right? So it's not like existent statement, but rather a construction. And postulate says that it's doable somehow, right? It validates this construction. No, anyway, however you interpret it as a rule or proposition, now again, it's not really important, but the important thing that it's not like to produce a straight line from a given point to another given point, right? That's simple. However you think about this logically, it's simple. And in that sense, we may say it's kind of basic. And that is not that simple. It looks like a theorem, right, that you might want to prove. And indeed, for one thing, we see even in Euclid, I think I mentioned that, but again, remind you that actually Euclid in his first book of Elements, he kind of pushes out using this fifth postulate as far as possible, right? So I don't remember now exact number, you can easily check, but just first fragment of this first book is does not rely on fifth postulate. So in modern terms, it's part of what sometimes is called, maybe today is outdated again, this term is 19th century term of absolute geometry, right? So something that is true independently of fifth postulate, right? And I think there are some epistemic reason, or at least they seem, how say, plausible. And indeed, now I go back to the book. Yeah, you see some attempts to prove this postulate as a theorem are mentioned, say, in this Proclus commentary to Euclid and some other places. There was one attempt due to Ptolemy, the author of Almagest, that I also mentioned. And so probably I will not comment on this. If you're interested, you may look. I uploaded this book, so you can read it. Or you can read it in Russian if you like. All right, so that's a long story, right? So that starts perhaps in Euclid's time already. We don't know exactly about, so evidences are very scarce, of course, about Euclid's time, but we can imagine, right? And that's, and I think with at least some reasons that even Euclid, they wouldn't consider this fifth postulate on the same footing with, say, first three postulates, right? So it was rather what Aristotle calls hypothesis, is something that you cannot do without, right? to do what you want, and at the same time you cannot be satisfied, say epistemically, because it's, you see, it's involves some sort of infinity if the sum of alpha and beta in our picture are close to pi, right? It's not really obvious, right? Intuition doesn't tell us anything definite, I would say, right? And so this idea that that principle could be proved is not so strange. It looks, so if you stick to this idea that first principle should be simple and kind of obvious, then of course you would want to prove this parallel postulate. Here, by the way, I would also make some distinction. What it could be in principle to prove this parallel postulate. And I would say that we shouldn't understand proof too narrowly, I think, right? Because it's one thing, of course, to prove it on the basis of other principles. So we just take this fifth postulates from the list of postulates, right? We consider it to be, say, conjecture, like Riemann hypothesis or something, and we use other principles and working, on the proof. And that's indeed, we know in 20th century, thanks to, say, Hilbert and other, we'll just talk about these people a bit later, that it cannot work. Okay. However, if you are more, say, liberal about what you call a proof, you may think about something a bit different, and that's different is, roughly speaking, replace or deduce proof, this parallel postulate, on the basis of some, say, new principle, which, unlike parallel postulate in its form that we find, say, in Euclid, would be more satisfactory, right? Would be simpler, more obvious, and that's, I think, it's quite a reasonable thing. At least all this Hilbert-style axiomatic approach does not close this possibility. And even I think there was some, I would say, success. So, usual story is that nobody really succeeded, and that was all working towards some kind of dead end, these ideas to prove it. No, however, I don't think it's quite true. I personally was particularly, say, interested of this work of John Wallis. That's already 17th century, so it's later. Yeah, that was another very important figure. Sorry. Yeah, probably I should also say, I'm sorry that I jumping so far. Here we find some interesting references in Proclus, as I just mentioned, and yeah, Simplicius. Yeah, some people, for example, replaced the notion.
Sorry, I have a question.
Yes, Lee.
I have troubles with connection in the first part of lecture, and I don't fully understand. Before I saw that Lobachevsky was the first one who saw that maybe there is a non-Euclidean world, and here you say, as I understand, and then there are already was philosophers and mathematicians who saw that maybe we can, I don't know, change the last postulate or get rid of it, and how it affects.
No, look, yeah, thank you for that. That's a very good question. No, we'll come to Lobachevsky. On Lobachevsky, I worked a little bit more, actually. and published paper recently, so we may talk more about Lobachevsky. So just answering your question, okay, I think perhaps it's first of all, Lobachevsky. We'll come to Lobachevsky, but just answering your question, Lobachevsky was not so definite about the fact that he's inviting some alternative geometry, No, at least, at the very least, he combined this idea of building alternative geometry with a more traditional idea to build a more general geometry, right? Lobachevsky's last writing, it's actually a book where he described it's called pan geometry, like like panoptica, pan in Greek means all. Yeah. So the idea was to generalize geometry. You see, to provide some general theory of geometry. And then, of course, he actually realized that somehow this general geometry kind of splits into some number, actually infinite class, right? If you think about, say, if you parameterize them by curvature in today's terms of geometries. And I don't think he had a really clear idea how it's all organized. Yeah, so no, we'll come to Lobachevsky. So I think
the question was pointed to the times before Lobachevsky.
Yes, of course, and that's what I just said. That this parallel postulate, even if we look into Euclid, right? No, we kind of see that it is not the same kind of thing that, say, first three postulates and fourth postulate, right? So it does not look like a simple self-obvious principle. That's the thing. And that's certainly not just my opinion or your opinion, but people, say, contemporaries of Euclid, or at least people mentioned in Proclus, you can a bit that was later than Euclid. So he refers to Ptolemy, I think, which is already first century. However, I repeat this fact that Euclid himself, it looks like he does not use this fifth postulate as far as he can, right? So there is a first fragment of first book is absolute geometry. It's without first postulate, which looks like he really wanted to distinguish between geometry that we can prove, or geometrical theory that we can do without fifth postulate, and other part that uses fifth postulate, right? And so attempts to prove it as a theorem are known since antiquity. And of course, when people tried to prove it, it was not attempt to make a new geometry, right? It was rather attempt to improve on geometry. And by the way, Lobachevsky started exactly with this. It was only later where he came to this idea that he's inventing some sort of alternative geometries. And even Lobachevsky never gave up this idea, right? And in a sense, I think that is right. Even, I don't know how you feel it, but I feel that all talk about Euclidean geometry, non-Euclidean, that's, by the way, was introduced by Felix Klein already in the late 19th century. It's a bit outdated. We would today say geometry, right? And it's kind of rich. There is many things in geometry, including different curvatures and things like this, right? But it's all geometry. And so I think all these people would think something like that, right? But certainly, probably people simply did not imagine this idea that you can either use, that you can negate this postulate, right? That's no, that's also wrong, by the way, because people usually did it, and many people did it, right? Trying to to get a proof by contradiction, reductio ad absurdum, от противного. So they would assume that fifth postulate is false and develop a theory trying to find a contradiction. And some people claim they did. Right now, today, we may analyze this. Actually, read the book. I think we don't have really time to look into it. But there are nice examples where people claimed, okay, I proved this postulate. Now, of course, we may look and say, not. You use this additional assumption, which is actually not justified. That's no. I probably want to show you just one. There is many important developments here. Yeah, I think this Borelli is very important. By the way, he is usually referred now as the inventor of, say, complex numbers, or imaginary numbers, as we say, but that's different part of his work. So they actually try to make like cases, different cases, and that's in a sense very similar to what later Lobachevsky did. Vitali, I think Sakeri was. I know. Okay, let's talk about Wallace, and then maybe Sakeri should be somewhere here. Yeah, Wallace, I think it's very interesting because he actually proved fifth postulate on the basis of this new axiom that similar figures exist. Actually, it's sufficient that just two pairs of, say, similar triangles exist for his argument. You don't, that is too strong. What is here that every, yes. And now he, no, if you like, we can just look into this proof. Yeah. So for these lines A and B, right, you, so this is like in Euclid's postulates. So you know that the sum of alpha and beta is smaller than 2 pi. Right? Is there the two right angles? Through A, you draw the straight line, and what is conditioned so that B and B prime form equal corresponding angles. Okay, so you're making like parallels. So you're making this B again, and now so you are supposed to show that this C exists. So what you're now doing, you kind of move this line AB to the right, right? And since you assumed that there exists a similar figure, right? So triangle with different, say, sizes, but with the same angles, okay? So you may claim that.
Sorry, what is the magnitude in this context? Как переводится?
Magnitude. Magnitude is no, say length. Magnitude is a general word for like length, volume, величина по-русски.
So it should be the triangle of the same area, length, etc.
No. He assumes that there are similar. Similar means the
on
length.
The previous page he writes magnitude. Arbitrary magnitude.
No, length meaning, ну как, similar figure, произвольной величины. Но имеется в виду
okay.
метрическая, а не углы. А углы те же самые.
Да, все, не понял, спасибо.
Okay. Yeah, so the argument that then you move this AB prime. It should be, I think it's not visible. It should be B prime here, right? So you move it, and then it say coincides with this similar triangle that that exists according to your assumption, right? Now moved continuously along the segment AB so that the angle which makes C remains always equal to beta. Okay, before it reaches its final point. Yeah, so it's actually, it's not the infinite line, right? It's the same length that this given. So he also thinks in terms of segments, like Euclid, right? Right. And so he looks at the moment when that would move. Yeah, so you have this here, this intersection point, like C here, right? That moves up. And so the argument is that this intersection point at certain moment would make a triangle. So you finally, the idea is that you move this AB prime to the position of B. Yeah, to that position actually, right? Right. So the argument that here you have this intersection point, and then it just moves up, and at certain point when your A coincides with your B, right, then you get a triangle, and so you get the intersection. And this, of course, is based on the idea that there is this class of similar triangles here, because what actually happens in hyperbolic geometry, right? In hyperbolic geometry there is no similar triangles, right? The angles of triangle depend of size of its sides, right? If you take so there is kind of absolute union there, right? If you fix your say geometry, right, or curvature, we say, right, then actually if you just know sides of triangle, then the sum of angles is a function of lengths of its sides, what is not the case in Euclidean geometry, right? So if you have very small triangle, then it's close to Euclidean, and if you take very big, then sum of angles becomes tends to zero actually, right? And there is this kind of limiting case which yeah, so in hyperbolic it looks like this. So if you get small triangle, it's more or less like Euclidean, right? No, even the sum is strictly smaller than pi. However, if you try to scale it, what's going on is something like this. So this sum decreases, all right? So it's become if it's sum of angles, so it's of trig that becomes smaller, and it's actually tends to something like this, right? So it's and actually there is a minimal surface. So its surface also. Yeah, I think there is minimal surface of before it becomes zero, right? There is some minimal constant surface. No, okay, you're more mathematician than myself, so you should check it. However, it's by the way, interesting geometry. Okay, we may look into how it works. Okay, yeah, but my point about Wallace, and I didn't publish the paper, but I think it's just observation that probably wouldn't be enough for making paper. But I think that in a sense, Wallace actually provided a proof, right? Because that idea that similar triangle exists, it's actually, well, I would say, more plausible than fifth postulate. I don't know how you would agree or not. It's also, it's not only plausible purely geometrically, but if you still not following Kant's line, but if you think about mathematics in kind of more applied way, if you like, right? Then of course it's very essential, say for architecture and things like this. Imagine you want to make a pyramid like this Egyptian people did, right? Which are still there. And you won't make a diagram. You say you want to calculate your pyramid. And the basic thing about this is a scaling, right? So you scale down your pyramid and making something on no paper was not available, but whatever, papyrus. Somehow you're making a representation of your building, geometrical representation. Of course, it does work if you ever studied. По-русски это называлось сопротивление материалов. Такая наука, я когда-то изучал. Resistance of materials. And then you learn that actually it does work that way, right? If you have small building and then you cannot just scale it up, right? Because it's weights, all this, how say, rigidity of construction is not linear. It would break your, so you something you can make a small thing, it does mean that you can just scale it up, right? Just like, by the way, I know that this was in living organism. You cannot just scale up a human body, say 10 times. It would become something unlivable in our conditions on the earth. Similar, but anyway, I think it's that very idea that you can somehow using this abstraction, and of course taking care about that abstraction, but still you can represent something big like a pyramid as something small like a picture in a book, right? That's something very essential about geometry, and perhaps that's the reason why we've chosen Euclidean geometry rather than, say, hyperbolic geometry as a kind of default geometry for so long. And then, so if we buy that argument, then we may say, okay, Wallace still managed to replace this fifth postulate by some other postulate that's more plausible in a sense. Right? Well, at least that's possible way of argument. Okay, let's Barelli. I'm sorry, I wanted to also say something about Sakari. Sakari. Ah, yeah, here is Sakari. It's, you see, it's also second part of 17th century. Yeah, that's very important. No, by the way, recall what I told you about Euclid, right? That's Euclid was very rare in history, really Euclid, and normally people will try to somehow to correct, to improve on Euclid rather than preserve historically original text. And that's that the name of this title. So he said it's Euclid. It's vindicated, right, or kind of saved from every error. So it just says it's improved Euclid. Yeah, or kind of new geometrical theory with universal geometrical principle. So you see, you can see in Sakari this idea that you also find in Lobachevsky, of course, just to generalize geometry, to provide some more general theory of geometry. And so what he did, he considered three different hypotheses. So his basic construction was quadrilateral, right? A figure with four sides, A, B, C, D. Yeah, here with the picture. And then how he defined that? Yeah, then you know that two angles are right angles, say these ones, left down and right down, right? Those are then two right angles and two equal sides, right? And then you know that AD equal to BC, so those are two angles, right? AB equal to BC, yeah. So this is determined, and then you kind of wonder what are these angles. Well, you see the construction is symmetric, so you may just ask a question about not about particular angle. These upper angles on the left and on the right. And yeah, he realized you can't really prove it without fifth postulates. And he just made what he called three hypotheses. First hypothesis that they are right angles, right? And this is Euclidean hypothesis. Another that they are obtuse, so they are larger than right angles, and that they are smaller than right angles. Okay, so he just very much like Lobachevsky did, if you like, but the different technique. Of course, here technique is much more primitive. Right, and then he proves actually that this hypothesis of obtuse angle, it leads to contradiction. No, in today's term, it would correspond to elliptical or spherical geometry. You see, so that contradicts the idea that two straight lines have a single intersection. So if you think about spherical geometry, right, then that doesn't work. So he dismisses the second hypothesis as contradictory, and then he works with this acute angle, which corresponds to Lobachevsky geometry. Yeah. And also, yeah, no, you can look. I think he also believes that he dismisses it after all, or maybe he kind of becomes uncertain. No. No, at least he's a forerunner, right? Предшественник, preceded. How much we can it's completely different. If the hypothesis of the acute angle, so that's correspond to hyperbolic case, is true in only one case, then it's true to every case. Now you see, he proves theorems like this, right? So should we think that he really developed non-Euclidean geometry? No, perhaps why not? He never, I think, pronounced this, right? But Lobachevsky also did not pronounce, no, he pronounced certain things, but you see, there is no kind of absolute difference, actually, right? So of course we wouldn't, he didn't go far, Sakari, right? That's his, in this geometry. However, he did something. He did something. So it's actually a question of interpretation of saying that he really, yeah. By the way, it was recently re-edited, his work, by my friend, actually, Vincenzo De Risi. So now we have it all available and readable. Yeah, so I wouldn't make actually any strong opinion and strong judgment on whether he really knew some non-Euclidean geometry, because I think it's not really serious question, right? Serious question what he did in fact, and how we interpret this and all of this. Yeah, you see, so he had quite a lot of results already. And of course, another person, okay, probably, yeah, it's Johan Heinrich Lambert. And I actually mentioned him, I don't know if you remember, not last week, because he was he corresponded that with Immanuel Kant. He was very prolific figure as a philosopher, as a physicist, and of course, as a mathematician, he was much more advanced than Immanuel Kant. However, his work on this problem of parallels, or theory of parallels, as they were called, it was only published after his death, already in, I think, 2 volumes. So those are edited, and then it's much more. It's actually very close to technique later used by Lobachevsky. Basic thing, he introduced what we call today hyperbolic trigonometric functions. That was, of course, something that people like Sakari didn't even think of, right? And that's, I think Kant would never understand really this. And that was a key thing. No, okay, I think I cannot describe the whole of construction, and probably I'll show a bit more in remaining time in Lobachevsky indeed. But key thing, there is this analogy with spherical geometry, right? Between hyperbolic geometry and spherical geometry. And spherical geometry was something well known and developed again for astronomical reasons, first of all, since ancient times, since antiquity. We didn't really spend a lot of time of this. Many laws.
Sorry, which geometry?
Spherical, spherical geometry. Spherical geometry, right? That was well known. Whether or not anybody looked at spherical geometry, as we would say after Gauss and Riemann, intrinsically, right? So whether they would think about geometry of a sphere, say, independently of how the sphere is embedded in outer space, is actually debatable question. I think a normal view is that they wouldn't think about it intrinsically. And indeed, that was great invention by Gauss, this notion of intrinsic geometry and intrinsic curvature. That, of course, we couldn't say that that was known before. It was not known, right? But on the other hand, they actually didn't have notion of space at all in geometry, right? So that notion of space is not part of geometry. It's rather philosophical. In philosophical writings, you can find stuff about space, like in Aristotle, even in Plato, right? But in geometry, the only way, say in Euclid, right, there is no reference to to space. There is only one point, and I think it's important, is this, that there is, of course, in last three books, right, which are 3D geometry, stereometry, there is concept of plane, Euclidean plane, and somehow Euclid, of course, assumes that everything he developed in first books for plane geometry, right, somehow is transferred to plane which lives in three-dimensional space, which is not trivial fact, of course. However, in this plane geometry, he just talks about figures, you see. There is nothing like plane as kind of ambient space. There is nothing like this. And in this stereometrical books, there is no notion of three-dimensional space. You see, there is notion of three-dimensional solid, three-dimensional object, yes, but not of three-dimensional space, right? And if you take this into consideration, then probably you may say that even if these people even called it spherical because it's about sphere after all, right? And sphere for them was something, you know, in space, in a sense. Though at least they also, you know, they made all this kind of models, say kind of astronomical. That, by the way, very interesting. One important was found not very about, I think, 10 years ago, was important archaeological discovery of complicated mechanism, which now with new methods could be much better studied than, say, earlier, thanks to new technologies. So again, it's debatable, you see. So they call it spherical, so it belonged to the sphere. And they didn't have explicitly this notion of intrinsic. However, particularly in astronomical concept, right? If you're thinking about, say, stars, observable stars, you think about stars in terms of angles, basically, right? And that's how you observe them, even without telescope or anything like. But you measure angles, basically, right? So in that sense, they had at least some way to think about this, you would say, intrinsically today. But that's spherical, right? But thanks to this, why this hyperbolic trigonometry, right? And spherical trigonometry was well known as well. No, maybe not in this form as we would learn it today already. Today we will learn it basically in 18th century form, Euler form, right? Then they would do this purely geometrically, much more complicated in a sense. But anyway, but Lambert observed that that kind of symmetry, that if you think about a sphere with imaginary radius, not with radius 1, but with radius I, right? Square root of -1. Right? If you think about such a square formally, then you actually obtain that sort of what Sakeri called hypothesis of acute angle. You see, so that's basically was Lobachevsky key to developing his geometry. In Lambert, no. Frankly, I kind of read that stuff, but did not that attentively to say how really close Lambert was himself. But anyway, these works were published after his death, and how much people really read these, I don't think so. At least Lobachevsky certainly didn't read these and made these discoveries independently. Probably Gauss read. I don't know, and I'm not sure all this is really well researched, because Lambert, for some reason, I think it's really important also for philosophy, but you see, not all people attract as much attention as some people like myself think that they deserve, right? And this is, of course, rather difficult, big project because it's all in Latin and no, not all. Those works, I think, if I remember correctly, were in German, but he also wrote in Latin. So it's you need a lot of students or something to do this work and a lot of money to pay. So it's not straightforward to make all this research. Maybe something is already done. I did not study that question exactly, right? So no, again, what written is more than a century ago by Bonella. I think it's still very, very good key. And I'm not sure that a lot of people did much work on Lambert later. No, okay, so we already have not much of time. So before talking of Lobachevsky, I want to mention Gauss and okay, Laplace. So many people contribute. Laplace, you see, it's a contemporary basically of Lobachevsky, 84, and he actually proposed his proof. So he believed he proved this fifth postulate. No, that was again based on assumption, additional assumption. Okay, let me skip this. This is probably less important. Legendre was the author of a geometry textbook, which later, by the way, was kind of paraphrased by Kisilev, and it was a source of, in a sense, even today's geometry textbooks. All right, yeah. No, so you can look, there are some interesting elementary geometry. Yeah, that person is important. Wolfgang Bolyai, and some people kind of contest and prefer to say that not Lobachevsky was the discoverer. However, they somehow together independently. So Bolyai was a son of a friend of Gauss, right? Who really, more or less, he followed this Sakari approach, but he achieved, say, much more. However, he sent this to Gauss, naturally, because his father, Gauss' friend, was kind of amateur mathematician. He was a lawyer, I think, but who also he wrote mathematical, he got some mathematical result. But Gauss was, by the way, one of the first professional mathematicians, kind of king of mathematics of his time, at least in Germany, right? And you can see why I don't see anything on Gauss himself. No, okay.
When you say professional mathematician, you mean that he earned money to live from the mathematics?
Yeah, yeah. And actually he was in university, had a position of mathematician, because that was also rather new. No, in different countries it depended. I think in UK, in Great Britain, that was very late when chairs on few mathematics were created. I'm afraid I think it was 19th century, maybe first, but I don't remember exactly now, but pretty late. It was probably first of all in France and in Germany. In France were also positioned in academy, which maybe was more important than in the university. Yeah. So I think in Germany that was also rather new, at least to that time where he was. And he also worked, he made a practical work in geodesy, right? So his task was to map the region of Hanover, of Gauss. And that's basically how he came to this understanding of, say, no, officially that was a geometry of curved surfaces. And that was a great achievement by Gauss, because you see, in a sense, you find the notion of curved surface even in Euclid. However, there's nothing about it, right? As I mentioned, John Barrow in 17th century. He actually made progress just about geometry of curved lines. However, geometry of curved surfaces before Gauss, I think, was really an infantry. It was nearly nothing. And Gauss actually came to this idea, imagine, so his task was, it's kind of hilly surrounding. There are hills, but not mountains. And that's important because it's at some approximation, say, smooth, right? And his task was just making measurements of distances at relatively, I don't know how exactly, a matter of maybe a couple of kilometers, right? What was available for him, how he could measure distances. But then he had to reconstruct from this data all these hills, how it looks like. And that's actually how he first thought about geometry of curved spaces, and he made a great achievement. So he defined what today is known as, I think it's called Gauss curvature, right? And that is a kind of curvature which is invariant with respect to isometry. So if you take a sheet of paper, right, and make a cylinder, it's still Gauss curvature 0, you see, right? So Gauss curvature is intrinsic. And if you take, say, half of a sphere, it's non-zero, right? It's positive. Because, and that's why you cannot just apply the isometrically the half sphere to the plane. And that makes all problem of cartography, of course. I don't know, you don't study, it's a kind of differential geometry, 19th century style. And I think it's pretty useful to study, even it differs from how differential geometry is studied today. However, I think it's very nice because it's very powerful and very much close to Earth, so to speak, right? Right. And actually, Gauss, as already his letter exchange reveals, he had some ideas about non-Euclidean geometry himself. Among other things, he supported Lobachevsky and supported his publication. However, he preferred not publish anything about this himself because he was kind of politically minded. No, I mean, scientific politics, right? Academic politics. And in one letter, he says that that would just make some outrage, so I better share this with some fellow mathematicians, but not with, say, wider public. And particularly bad that worked for Wolfgang Bolyai, because he replied to Bolyai when he sent him his ideas, that he, Gauss, knew all of this, was nothing new to Gauss, and I rather advise not publish it. And apparently that really, this young man, Bolyai, took it very, very personally and seriously, and indeed never published anything. So it was kind of crisis for him, as some biographer says. So that was really a bad thing for. But Lobachevsky did not ask Bolyai permission, or sorry, Gauss permission. Okay, let's talk a little bit now about Lobachevsky. I think we are short on time. I also wanted to say a couple of words about Riemann, which I think is very important to that story, but okay, maybe next week. For Riemann, now I won't. Yeah. Can you see PDF now?
Yes.
Yes.
Yeah, I have here, I did a paper. No, it's not nothing really very new in this paper about Lobachevsky. Actually, I kind of objected in this paper against the way the Lobachevsky geometry is usually presented these days when we talk about axiomatic system or right, and models, because Lobachevsky himself didn't think about such things. And I think it's still interesting to look how he was thinking about matters, right? Even if this later view is also, I think here I made just in a footnote, what he really did. So he first made a kind of manuscript called Geometry, which was supposed to be a textbook, and that was in 1823. His biography is very interesting, and it's very well written. There is books by Veniamin Fedorovich Kagan, who was actually, I think, also very interesting, important figure. After the war, he was chair of differential geometry in Moscow, Mikhmat. And among other things, he was main editor of edition of all Lobachevsky works, which were edited and now are edited. And also he wrote actually many books, and one of which just called Lobachevsky. There is biography, everything. I think it's still the best written about Lobachevsky. There is something new. So I more or less rely on this Kagan as a source. So, no, okay, I probably will not talk about his biography, even if it's very... He was taking this new university in Kazan, which then was only recently founded. And then he had spectacular career, because at a certain point he was nearly expelled for drinking, for kind of bad behavior and things. And very soon after, he became a rector. And that, of course, was because of changing minister, changing the Tsar in St. Petersburg. So, but okay, I probably leave it. Otherwise, we really don't have time to talk about mathematics. So that was just his first work in geometry. By the way, he published other stuff, not only in geometry, but I now focus what he did in geometry. That was kind of rejected, and indeed, maybe for some good reasons at least, right? Then he made this bigger project, right, Foundations of Geometry, which already includes this stuff about so-called non-Euclidean geometry. And by the way, that was not, again, he had another idea in geometry, right? His idea was, actually his philosophical motivation was to make geometry more physical, so to speak, right? Somehow to narrow the gap between, say, abstract mathematics and application. He really wanted, he was very much empirically minded and followed, as Kagan says, in that sense, actually what Lambert, it's one of the author of so-called Diderot Encyclopedia. And he had a very radical view, actually, on geometry, that it shouldn't follow Euclid, it doesn't need axioms, but it should be more like practical. And I think it's very interesting, you know, because at least in Lobachevsky, and Lobachevsky clearly followed this, say, suggestion, and that, of course, was related to, again, politically to French Revolution. And in Russia, it was politically laden with revolutionary ideas. And but that was example where this idea to make something more practical was really interesting. You see, in a sense, it gave us non-Euclidean geometry. And it's important that it was not about axioms at all. If you look, there is no axioms in the usual sense. So he was kind of anti-Euclidean. And this non-Euclidean geometry was part of this. All right. Then he wrote this paper, Imagined Geometry, which was published then later in French. And I think it's a little bit misleading title, because what he really meant by imaginary, it's not that it's kind of non-physical, because he believed it should be physical. That's important. He used astronomical tables trying to check whether geometry of real observed space is Euclidean or not. No, then he realized that just precision is not sufficient to make any judgment. Right? However, certainly he didn't think about this non-Euclidean geometry as something, you see, all existing in mind or some special world. No, imaginary he called for simple reason, because in this work there is no single diagram, right? It's all analytic. So the argument was that you might forget about geometry and just use the kind of calculus that I propose, which is basically this, what I already mentioned, hyperbolic trigonometry. And then, by the way, was a supplement to this paper where he calculated a lot of integrals that people couldn't calculate earlier. So it's just using analytic technique, and in that sense, imagine that you may imagine some geometry, or if you somehow don't want to do that, you can just stick to this analytic. Yeah, this is application imagine geometry to some integrals. Okay, yeah, then he kind of started similar project in new foundation of geometry. But his key paper that was written in German, and by the way, never translated. This he Imagine Geometry he wrote, I think, first in French, then translated himself into Russian, and that he just wrote in German. So Russian translations are made already by other people. And this is actually key paper, which was published, I think, in this Mathematische Annalen, if I'm not German version, yeah. I didn't put reference here, right? I should say. Or was it Crowley Journal? Yeah. No, that was Géométrie Imaginaire. That was the so-called Crowley Journal. So this other German paper was in Mathematische Annalen, which was actually, and still is, I think now it's less important journal than it used to be, but at that time it was most important. And of course, Gauss somehow, my understanding, he was kind of indirectly a reviewer, so he much promoted Lobachevsky. By the way, Gauss was also, he was studying Russian. Some people he was studying just to read Lobachevsky. I don't, what I found myself that he studied Russian for reading Pushkin and not Lobachevsky, which was, of course, much more reasonable motivation, because after all, Lobachevsky wrote in German, and actually I think it's still the best paper. So it was the best journal of the time and the best paper by Lobachevsky, because really it's very concise and it's focused, and it has also this geometrical part and analytic part. So unlike this earlier paper, which was purely analytic. Yeah, no, of course, it's not very easy reading, you see. So if you take, there are very nice commentaries by Kagan, because there is a lot of kind of, rather laborious elementary geometry reasoning, which it's not so straightforward, at least on my part, to realize. But in this paper, I just wanted to show how, roughly speaking, how Lobachevsky thinks about non-Euclidean geometry without axioms, what that would be. And that means that he actually thinks about intuitively, very much like we think about Euclidean geometry. So it's, in a sense, goes against this view that, say, our intuition is kind of Euclidean, So the only intuitive access to, say, Lobachevsky geometry would be to make some sort of Euclidean model of non-Euclidean geometry. I think that is just wrong. We may develop that kind of hyperbolic intuition, at least at first steps it really works. So it just, if you follow this paper that I recommend, yeah, I should probably upload, I didn't do that yet, just a copy of this Lobachevsky paper. Its English translation exists for a long time already. So I'll do that. But really, what I think made his name, what allows to call Lobachevsky kind of discoverer or father non-Euclidean geometry, was his calculus still. I think mathematical, that was indeed more important. Basically what he did, it's interesting because rather than finding a model of hyperbolic plane, what he really did, he found in hyperbolic space that he describes kind of intuitively, he found a model of Euclidean plane. So it's kind of, it's actually should be surface which is orthogonal to a sheaf of parallels, but parallels in Lobachevsky sense. You see, it's not just something that straight line which do not intersect, but they're roughly speaking limiting straight lines. I can show you just in a picture. That means roughly the following. So if you have a straight line, given straight line, and you have a point, right? And now you imagine it's not just one, but say two lines which go through this point and which don't intersect our given line, right? And then first observation made by Lobachevsky that there should be some sort of limiting case, right? Because you see, for example, you can go further. Well, let's this point A, this is B. And of course, you can form a secant, right? So you can take another point C, however far from A, and then of course you have a line through B and C, right? So all these lines they are bounded by certain line from above, and then if you fix distance here, say D, then you have an angle. So you have some kind of function, we'll say D of alpha. And so if you fix distance, you have characteristic angle. If you fix angle, you have characteristic distance. That, by the way, where this absolute unit of length, so-called, comes from, right? For example, you can take a triangle such that sum of its angle, say it's precisely half of pi, for example, right? And then the size of such angle will give you this absolute unit of length. Or simply just in that construction, you fix alpha and D becomes your unit of length. You see, so yeah, and Lobachevsky calls parallels this kind of limiting parallels, right? Such that anything under that line already intersects my AC. Okay, so there are precisely two parallels in that sense, not more than one, but precisely two. Then, by the way, which is not quite obvious, he shows that it's transitive, so parallel to parallel is parallel. It's not obvious, but it is theorem. He proves that. And then imagine you have what? You have a sheaf of parallels in that sense, and you consider a normal surface a surface which orthogonal to each parallel, right? And then he called it Ori sphere. Ori sphere. Ori from horizon. Ori sphere. Okay. And then horosphere. Horosphere. It's kind of horoscope, the same word. Horosphere. Horosphere. And then he proves that this horosphere is intrinsically Euclidean. So you may prove fifth postulate on this horosphere. That's actually what. And then he recalculate usual trigonometry and obtains what we call today hyperbolic trigonometric functions, which, as I told you, in some form were already in Lambert. And that actually gives him analytic apparatus, which fully describes the whole thing. That's his basic achievement, you see. No, and of course, ideologically, I think it was also important, right? That he kind of insisted that I don't want any longer to prove this postulate, but I kind of invented new geometry. But first of all, this new geometry is kind of general geometry, which simply includes Euclid's geometry as a special case. However, it's general in this special way, right? In a sense, it just splits into class of geometries that depend on this alpha. And somehow things in order were put later already by Felix Klein. Maybe I continue. I think we should stop now, right? Continue the next time. Because one thing that Lobachevsky did not realize, and that I think it's really kind of failure, as far as I know, he did not see the relationship between his work and this Gauss work on curvature. You see, so he did not relate that to theory of curved surfaces or anything like this. And that, of course, was limiting. So all these names like hyperbolic, spherical, and parabolic, Euclidean would be parabolic. They were introduced later by Felix Klein already on the basis on Riemann's work, and by the way, on projective geometry, which also plays a role there. But maybe it's no, we may continue a little bit next week. I think I should stop now, right? So if you have some questions, please ask me. I'm not in a hurry, but probably some of you are. Yeah. No, I think it would be nice if you read a little bit, then we could discuss, because just present, you see, we have actually little time. So if I try to combine this general facts with some details, that wouldn't work. So if you read about some details beforehand, we may discuss them. And that maybe would make it a little bit more focused and concrete. So at least about Lobachevsky, I can also, because I kind of work on him, and now we have a new project towards this Congress of Mathematicians on Lobachevsky. So, yeah.
Okay.
No, okay, so again, if you have any questions concerning your works on anything, just write me emails. And then, okay, that's it. Ankit, Svetoslav, do you have questions?
No.
Okay. Okay, so I'll upload some, I'll try to find this English translation, should be in my computer. So I really recommend, even if it would take time, but even if you don't have time to read it in all details, you see how it is. And I think it's even much. I also have a paper by John Milner, you know, that Voevodsky got Fields Medal for proving Milner conjecture. And so this John Milner wrote, I think already time ago, maybe in 80s, if I remember correctly, some really interesting paper on Lobachevsky, which doesn't go from the standard notion of say axiomatic system, which, as I say, were at least quite alien to Lobachevsky. But he made some really interesting comment on this analytic part, which I don't know if I'm not sure I can understand all of it, but probably some of you who work on algebraic geometry may appreciate even better than we might discuss it. It looks kind of exciting. Yeah. He even introduced some notation, I think L, I mean John Milner for Lobachevsky, and that's very, how say, special reading, because I think no historian reads Lobachevsky in that way. That makes, I think, it's very interesting. Okay, so then see you next week. Bye-bye.
Goodbye.